Hey everyone, welcome back to the deep dive. We've gotten some really interesting stuff from you lately about what happens when you're dealing with clustered data, but you just don't have a huge number of those groups to work with.
Yeah, this is a super important question that a lot of researchers run into, right? How much can we really trust the results that we get from those, multi-level models? Some people call them hierarchical linear models or mixed effects models. Especially, like you said, when you're working with a smaller number of clusters, understanding the limitations is really key.
Yeah, and it comes up so often too.
It does.
So many different areas have clustered data students in classrooms,
Hmm.
patients in hospitals, employees in teams. I mean, I could go on and on.
Yeah.
And multi-level models are really the way to go when you're analyzing data like
Right.
that, right?
Hmm.
Because they get at the idea that, data points within the same group are probably going to be more similar to each other
Right.
than to, data points from different groups.
Right.
But as the research that you send points out, having too few groups can really mess with how reliable those analyses are.
Yeah.
So in this deep dive, we're going to really try to distill the core concerns and give you some actionable recommendations. We've been digging through academic articles, looking at the methodology, the impact of sample size, simulation studies, and existing literature, all to bring you the most important insights.
Yeah, and I think you're right. It's really important to distill these down because some of these papers can be pretty dense,
That they can.
but they have really important information. So, what is a multi-level model? What is it actually doing? Well, at Theramart, they're designed to account for that hierarchical structure in your data, right? They acknowledge that, for instance, student test scores within a single classroom will likely be more related than scores from students in completely different classrooms.
Yeah, and the big thing is if you ignore that clustering, right? Like if you just use a regular old single level model, like ordinary least squares regression or
All
something,
right.
you're kind of asking for trouble.
Yeah.
The biggie is that you'll underestimate your standard errors.
Yeah, exactly. And so when your standard errors are too small, what that means is that you're more likely to conclude that you have statistically significant finding when really you don't. So that's called an inflated type I error rate, right? You might think you found something when you haven't. So the nice thing about multi-level models, or MLMs, is that they address this by including what we call fixed effects, which represent the overall relationships you're investigating, and random effects, which capture the unique variation across your different groups. And then we also look at things like variance components, which tell us how much of the total variability exists at each level within groups and between groups, and of course standard errors, which are really just a measure of the precision of all these estimates.
So the MLM, it's the right approach for the data, but now let's get into the real nitty-gritty of this. What happens when we just don't have that many clusters?
Right.
Because the research you sent really hammers this point home. It's not just the overall number of data points that matters, it's the number of clusters, those groups.
That's right. One of the big reasons is that the maximum likelihood estimation, or ML estimation, that we use a lot of the time in these models, it's what we call asymptotically unbiased. So what that means is as your sample size gets bigger and bigger, the closer and closer your estimates are going to get to the true value.
Okay.
But when you only have a small number of clusters, those estimates, they can be off.
Yeah, and I remember seeing some of those rules of thumb too,
Oh,
right?
yeah, definitely.
Like Krefft's 30-30 rule, at least 30 clusters and 30 observations in each. Then there's Snyder's and Bosker, who suggest you should have at least 20 clusters. And Hawks also has his recommendations, like 50 clusters with 20 units each for cross-level interactions. He even suggests going up to 100 clusters with 10 units each if you're really focused on those variance components.
Right, and those are really helpful guidelines to aim for.
Hmm.
But in the real world of research, as Dedrick and colleagues pointed out in their 2009 review, a lot of studies that use MLMs don't even get close to that 30-30 rule,
Oh, wow.
which suggests that maybe researchers aren't always aware of these recommendations, and I think this is more likely, it's really tough to actually get that many clusters when you're out there doing research. So,
Yeah.
your model might run and it'll spit out numbers, but if you don't have enough clusters, those numbers might not be giving you the right information.
They might not be reliable. So, okay, a small number of clusters, it can cause problems.
Yeah.
But can we, get a little bit more specific? How does it affect all the different pieces of information that an MLM gives us? Let's start with, those fixed effect point estimates.
Yeah.
Those, the overall relationships we usually really care about measuring. What happens to those?
Well, the interesting thing here is that those fixed effect point estimates are actually the least sensitive to having a small number of clusters.
Oh, okay.
Most of the research shows they're pretty much spot on, even with as few as 15 clusters, sometimes even fewer.
Okay, so that's good. So we just want to know the average effect of something like, say, how a new teaching method affects the average student's test scores.
Right.
The point estimate itself might be pretty accurate, even if we don't have tons of classrooms in our study.
Exactly. But there is one little thing to keep in mind. If you're looking at fixed effects that involve what are called level 2 predictors, so characteristics of the groups themselves, like how much funding a school gets,
Hmm.
those might start to get a little wonky if you have less than 15 clusters. Like they might get overestimated a little bit.
Okay, so the actual point estimates themselves are usually pretty good, but what about their standard errors?
Right.
Because those are super important for figuring out if the effect we're seeing is actually, statistically meaningful. What about those?
So this is where having a small number of clusters can really trip you up. Those standard errors for your fixed effects, they tend to be too small, underestimated when you don't have enough clusters.
Gotcha.
And you're especially likely to run into this problem when you are using the, more standard estimation methods. Like Moz and Hawks found that back in 2004 and 2005, they found that you really need something like 30 clusters to get standard errors for your fixed effects that are, right on target.
And we talked about this earlier, but just to reiterate,
Yeah.
underestimating standard errors, it's a bad thing because it makes it more likely to get a false positive.
Right.
It's like thinking you found a real effect when
Yeah.
really there isn't one.
Exactly. But there is something you can do about it, especially for those continuous outcomes. There's this thing called the Kenward-Roger adjustment, and it's actually pretty powerful. Like studies by Kenward and Roger and Baldwin and Fellingham and Farron and colleagues and Bell and others, they've all shown that this adjustment can really help. It makes those underestimated standard errors much closer to what they should be, which means you can trust your p-values a lot more.
That's great. Can you walk us through, how the Kenward-Roger adjustment actually works?
Sure. So basically, it makes a correction to the way the variability of your fixed effects is estimated, and it also adjusts the degrees of freedom that are used in your statistical tests. What this does is it takes into account the extra uncertainty that comes with having fewer clusters. So you end up with standard errors that are more realistic and p-values that are more trustworthy. It's kind of like it helps to keep your statistical tests honest when you have a small number of groups.
So it's basically like a way to boost the reliability of our tests when we don't have that many clusters, at least when we're working with continuous outcomes.
Exactly. Now, the main thing to remember is that it's not available everywhere.
Okay.
It's mainly in SAS software, particularly in something called the proc mixed procedure. Now, there is an R package called PBK test that can do it for certain models, but the documentation says it hasn't been tested as much.
Okay, so a potential fix for continuous outcomes. What about binary outcomes? Like, when we're looking at things like, did something succeed or fail, yes or no responses, but within clusters? Like, what happens there?
So with binary outcomes, things can get even trickier when you have a small number of clusters. The standard errors tend to be even more biased, especially when the clusters themselves are small, like less than 10, or when you have a binary predictor that's, really unbalanced, meaning most of your data is in just one category. And in these situations, even the Kenward-Roger adjustment might not be enough. You really might need a lot more clusters, like even up to 60 sometimes, to get reliable results, especially with those really uneven binary predictors.
So that's a really important thing to keep in mind if you're working with binary data that's clustered.
Mhm.
Okay, let's move on to those variance components. We've got the level 1 variance, which is all about the variability within our groups, and the level 2 variance, the variability between our groups.
Right.
So how does a small number of clusters mess with those?
All right. Well, the good news is that the level 1 variance point estimate seems to be the most resilient out of all the estimates. Research from Brown and Draper, Moz and Hawks, Muleman and Billiot and Stegmuller, they all suggest that it's barely affected by the number of clusters.
Oh, good.
So you can usually feel pretty good about your estimate of how much things vary within groups, even if you don't have a ton of clusters.
That's a relief. But what about the level 2 variance point estimates? Like the variability between those clusters, that one feels like it would be more sensitive to the number of groups we have.
And you'd be right, it is.
Oh.
When you use full maximum likelihood, or FML estimation, which is pretty standard, you often see a downward bias in your level 2 variance estimates when the number of clusters is small, especially below 30.
Okay, so if we're using FML and we have fewer than 30 clusters, we might be underestimating how different those groups really are from each other.
Yeah, that's right. But for continuous outcomes, there's this other estimation method called restricted maximum likelihood, or REML, and this can actually be really helpful. Brown and Draper found that REML tends to give you level 2 variance estimates that are less biased when you have small clusters. Essentially, what REML does is it tries to estimate the variance components in a way that's less influenced by the fixed effects. It's a pretty subtle difference, but it can make a big difference, especially with smaller samples. It's important to note, though, that even with REML, if your cluster sizes are really tiny, you can still sometimes overestimate the level 2 variance. Clark and McNeish found that.
Okay, so REML is generally better for level 2 variance, at least for continuous outcomes.
Right.
What about binary outcomes, though? What should we do in that case?
So for binary outcomes, if you're using methods that try to approximate FML, things like adaptive Gaussian quadrature, you can actually end up with a pretty big positive bias in your level 2 variance when you have a small cluster size, again, usually below 30. But what's interesting is that there are these things called REMML analogs, like penalized quasi-likelihood or PQL, that actually seem to do a better job when you have fewer clusters for binary outcomes. Austin's research in 2010 showed that. So yeah, choosing the right estimation method is really important, especially when you're dealing with variance components in binary data.
Absolutely. Okay, now let's talk about the standard errors of those variance component estimates.
Yeah.
How are those affected by the number of clusters?
So this is where things can get really, really tricky. The level 2 variance standard errors, they're the ones that are the most affected by having a small number of clusters. Rodenbush and Brick found that. And lots of studies have shown that you can have really high non-coverage rates, meaning your confidence intervals are probably missing the true value, even when you have a decent number of clusters. Moz and Hawks and Mollman and Billiot both found that. So basically, if you only have a few clusters, those standard z-tests for your variance components, they're really not that reliable.
Okay, so if we run our analysis and it looks like we have a significant level 2 variance based on that z-test, but we only have like a handful of clusters, we should be really careful about interpreting that result.
Exactly. The research really suggests that you should be super cautious about those z-tests for variance components when you don't have a lot of clusters. And actually, there are other ways to test variance components like likelihood ratio tests or using something called a 50-point fifth Vero mixture chi-square distribution. Fitzmaurice and colleagues and Molenbergs and Verbeek suggest those, and those are generally better choices in this situation.
That's really helpful to know. Now, before we jump into potential solutions, I wanted to touch on model convergence, especially with binary outcomes and multi-level models. What do we need to be aware of there?
Yeah, that's another thing to watch out for. When you have a small number of clusters, especially if those clusters are small themselves and your outcomes are unbalanced in a multi-level logistic regression, you can run into problems with your model converging. Basically, what that means is the statistical software you're using, it might have trouble finding a stable, reliable solution. Like Moinadian and colleagues found that, if you only have 30 clusters and the sizes within those clusters are small, the convergence rates can be pretty bad.
Hmm.
Generally, the more clusters you have and the larger those clusters are, the better your chances of that model actually converging properly.
So that was a lot of info about the problems that can come up. And you also sent over some info about this simulation study that really drives these points home. Could you tell us a little bit about that?
Yeah, so McNeish and Stapleton, they did this really neat simulation. They used a simple random intercept model with one predictor at level 1 and a continuous outcome. And they varied the number of clusters from a tiny 5 all the way up to 1,000. They used two different cluster sizes, 20 and 50, and they stuck with FML estimation.
So what did they find? What were the big takeaways from that simulation that really illustrate the issues we've been talking about?
Well, their results pretty much lined up with everything we know from all the other research. They found that those fixed effect point estimates, they really weren't affected by the number of clusters. But when it came to the fixed effect standard errors, there was definitely bias. Like they were underestimated, and those confidence intervals didn't capture the true value very well, especially when there were less than 20 clusters. And again, those level 1 variance point estimates, they were pretty rock solid, showing almost no bias across the different numbers of clusters. Now, when they looked at the level 2 variance point estimates from that FML method, they started to see that downward bias when the cluster count was less than 30. And the most dramatic thing they found was with the level 2 variance standard errors. Those were really messed up, even with 100 clusters. That just shows how unreliable those z-tests can be for variance components, especially in these situations.
Yeah, that simulation really makes it clear how easily we can get biased results when we don't have enough clusters. So let's say we're stuck in a situation where we have cluster data, but we just can't get that many groups. What can we do?
Well, luckily, there are a few things we can try.
Oh, good.
First, if we're dealing with continuous outcomes, we've already talked about using RML estimation instead of FML. That can really help to get better variance component estimates when you're short on clusters. And for those binary outcomes, it might be a good idea to look into estimation methods like RPL or PQL, since those tend to be less biased than the methods that try to approximate FML.
And let's not forget the Kenwood-Roger adjustment for continuous outcomes, especially if you're using SAS.
Oh, yeah, absolutely. That can be a lifesaver for getting standard errors that you can actually trust and for keeping those type I errors under control.
What else is out there?
There's this technique called bootstrapping, and the literature suggests it can be really useful. What you do is you basically resample your data over and over again, and that gives you a more stable and accurate idea of how much your estimates might vary just by chance. Researchers like Buttar and Lahiri, van der Leiden and colleagues, and Gonzalez-Manteiga and others have shown that bootstrapping can be super helpful for multi-level models with smaller sample sizes, and you can actually do it in software like MLWM.
Okay, so bootstrapping, another tool to keep in mind. Anything else?
All right, so let's say you have a very small number of clusters, like 20 or fewer, but you have a lot of observations within each cluster.
Okay.
And let's say you're mainly interested in testing hypotheses about the fixed effects at level 1, not so much those variance components or level 2 predictors.
Yeah.
In that specific case, you could actually try dummy coding your clusters in a plain old OLS regression.
Interesting.
And if you use what's called effect coding instead of the usual O1 dummy coding, you can actually get fixed effect estimates that are pretty similar to what you'd get from an MLM. Gardner and colleagues and Snyders and Bosker have talked about this.
So a potential workaround for very specific research questions.
Yeah.
Now, I know a lot of these papers also mention Bayesian MCMC estimation.
Oh, yes. Bayesian methods. They're showing a lot of promise, especially for getting more accurate estimates, even with a very small number of clusters. Like Austin, Brown, and Draper, Stegmuller, and Gelman, they've all presented some pretty compelling evidence. The cool thing about Bayesian methods is that they don't rely on those same large sample assumptions that traditional methods do. But of course, there's a catch. You have to be really thoughtful about choosing those prior distributions, especially for those variance components, which can be tricky.
So a potential path forward, but with its own, complexities. It sounds like we've made a lot of progress figuring out these challenges and coming up with solutions.
We have.
But I know the research you sent also mentioned some areas where we still need to learn more.
Definitely.
What are some of those unanswered questions that are still out there?
So most of the research we have now has focused on two-level models. But we need more research on how small sample sizes affect three-level models, or even higher. Those are really common in areas like education or organizational research. And we also need to dig deeper into how well different estimation methods work for binary outcomes when our models get more complex. More research on Bayesian methods, especially how to pick the best priors for those variance components, would be awesome. And we need to look beyond continuous and binary outcomes too. Like what happens with count data, nominal outcomes, ordinal outcomes, how are those affected by small cluster counts? And one more thing. Most studies assume a balanced design where all the clusters have about the same number of observations. But in real-world research, you often have unbalanced designs. So we need to understand better how that affects our results compared to balanced designs.
So yeah, it sounds like there are plenty of avenues for future research to
Yes,
explore.
yeah, lots to do.
As we wrap up this deep dive, what is the absolute most important takeaway you'd want listeners to remember?
I think the biggest thing is to be really cautious when you're interpreting those MLM results if you only have a small number of clusters. While the fixed effect point estimates themselves are usually pretty stable, those standard errors and especially those variance component estimates, they can be really biased. So don't take them at face value.
And just to recap those practical tips, we talked about using REML for continuous outcomes, remembering the Kenwood-Roger adjustment in SAS if your outcome is continuous, and just being super aware of those extra challenges with binary outcomes and when testing those variance components when your cluster counts are low.
Right, and don't forget about those Bayesian methods.
Yes, Bayesian methods.
They could be a really good option in certain cases, but you really have to think carefully about those prior assumptions.
Yeah. But ultimately, even with all these tools and techniques, the bottom line is still that larger samples are better, right?
Oh, yeah, for sure.
Especially more clusters. That gives you more statistical power and helps you be more confident that your model assumptions are actually holding up.
Absolutely. All these techniques we talked about, they can help, but they're not going to magically fix everything. You really need a decent number of clusters to start with.
So here's something for all of you to think about as you go forth and analyze your data. What kinds of limitations are you facing when it comes to the number of groups you can actually get?
Right.
And how can what we've talked about today help you make better decisions about your analysis and how to interpret your findings? And if you're really interested in diving deeper, I encourage you to check out some of those methods we've discussed: RAML, Kenwood-Roger, bootstrapping, and those Bayesian approaches. And always be mindful of the sample size recommendations for your specific area of research. Thanks for joining us for this deep dive. We'll see you next time.